So if you've spent any time at all working with large language models in production, you know, the one big ongoing battle.
Oh, yeah. The fight against hallucination.
Exactly. LLMs are just these magnificent tools, but the second they confidently spit out something that's totally inaccurate, all that credibility just, you know, evaporates.
Especially when the facts really, really matter. And the industry's first, and I guess still the gold standard answer to that has been retrieval-augmented generation.
Right. Pull in outside knowledge to ground the model.
Yep. But even that, as powerful as it is now hitting a pretty serious wall, a structural ceiling.
And that wall, that ceiling, it's all about how it processes information, right?
Yeah.
It's just looking at these big unstructured blocks of text.
Right.
Okay, so let's unpack that. Our deep dive today is into something called GraphR1. And this feels like a really significant evolution in this space.
It is. It's an agentic framework, a new type of GraphRAG, that's designed from the ground up to solve those structural and retrieval problems using, and this is the key, end-to-end reinforcement learning.
Okay, so the mission for us today is to really get into how GraphR1 pulls this off.
I think so. It's really about three key innovations working together. Making the knowledge structure more efficient, making the model's interaction with it more dynamic, and then using this outcome-directed learning to train the whole thing.
And the goal is a big jump in reasoning accuracy on really tough benchmarks, like hot pot QA.
That's the promise.
All right, so we have to start at the root of the problem. Before we get to the solution in GraphR1, let's just set the scene. What are the foundational issues it's trying to fix, starting with that standard chunk-based RAG?
Well, standard RAG, it fundamentally relies on embedding and then retrieving these chunk-based text blocks.
Just paragraphs, essentially.
Pretty much. And while that's fast, computationally speaking, it critically misses the structural semantics.
What now?
The relationships, the complex connections between all the different facts and entities inside the text.
Ah, it's like having all the Lego pieces scattered on the floor. You have the blocks, but you have no idea how they're supposed to connect.
That is a perfect analogy. You lose the blueprint.
I see. Okay, so to fix that, researchers brought in traditional GraphRAG. The idea was to model the knowledge as a graph to bring back that structure. But that just created a whole new set of problems.
It really did. Expensive problems. Traditional GraphRAG methods, they ran into three major challenges that just limited how scalable they could be.
Okay, what was number one?
The first and the most immediate was the high cost and the semantic loss that happened during construction.
Wait, just building the graph was expensive. Why?
Because to turn natural language into a clean graph, you needed to use these huge LLMs to do really intensive analysis and extraction.
So you're using an LLM to prep data for another LLM.
Exactly. It was super expensive computationally, and ironically, you'd often lose some of the original meaning. You'd get semantic loss because that extraction process just wasn't perfect.
Okay, so that's a huge hurdle. What was the second challenge?
The second was its reliance on fixed retrieval.
Fixed retrieval.
Yeah, the existing methods, they were all designed to grab all the knowledge they thought they needed in one single fixed step before they even started reasoning.
That sounds like a one-shot poker hand.
It is. If you didn't grab the exact right facts on that first try, your whole multi-step reasoning attempt was basically dead in the water.
Wow. Okay, and the third issue?
The third was that it was still so dependent on the LLM's long context ability.
Ah, so even after you get the graph data, you're just feeding this massive, messy context into the model and hoping for the best.
Precisely. It made the output quality really unstable and totally dependent on how good your prompt was or how massive your model was. So GraphR1, it had to tackle all three of these things at once.
Okay, let's dive into the solutions then, starting with that first bottleneck.
Yeah.
The cost and the structural loss. This is where it gets really interesting for me. GraphR1 introduces something called lightweight knowledge hypergraph construction.
Right.
So first, what on earth is a hypergraph, and what makes this process lightweight?
Okay, so a standard graph models binary relationships. You have node A connected to node B. A hypergraph is just richer, more powerful. It uses what are called hyperedges to connect multiple entities all at once.
All based on a single piece of text.
Exactly, usually a complete sentence or a clause. So it naturally captures these higher order relationships that are much more like how knowledge works in the real world.
So if I have a sentence like, person X married person Y in city Z, a hyperedge would connect all three of those things at once instead of breaking it into separate pairs.
That's exactly right. You preserve the whole fact. Now, the lightweight part is all about the cost. GraphR1 just streamlines that whole extraction pipeline. It avoids the massive LLM overhead its predecessors had.
And the source material has a direct comparison on this,
Yep.
right? The cost per 1,000 tokens.
It does. It shows GraphR1 is substantially cheaper. It's about $2.81 versus over $4 for its predecessor, HyperGraphRAG.
So it's cheaper, but is there a trade-off? Do you lose some of the richness or the accuracy of the graph?
And that's the key finding. Apparently not. The sources show it maintains this massive, rich structure. We're talking over 120,000 nodes and nearly 100,000 edges while cutting costs.
How?
Because the system is designed to use that structure strategically. And that brings us right to the second big innovation.
Which solves the fixed retrieval problem.
Right. So once you have this efficient hypergraph environment, the next step is changing how the model interacts with it. GraphR1 treats retrieval as a multi-turn agentic interaction process.
Okay, so it's not a database lookup anymore.
Not at all.
The model is acting more like a human researcher. It's thinking, it's searching, it's reevaluating its own plan.
Yeah.
It's moving completely past that old one-and-done retrieval method.
That is the core difference. The agent is in this continuous loop. Think, retrieve, rethink, generate.
A loop?
At every single step, the agent looks at what it knows and decides what to do next. It has 4 options.
Which are?
It can think, which means reflecting on what it's missing. It can generate a query. It can retrieve from the graph. Or finally, it can answer.
Can you walk us through that? Give us a concrete example of how that multi-turn system actually works.
Absolutely. The source gives a great one. It's a complex 2-hop question. Who is the spouse of the director of the film in memory of Sergo Ordzhonikidze?
Okay, a standard RAG would probably struggle with that.
It would. But GraphR1, step 1. The agent takes a thinking action. It reasons internally. Okay, first I need to find the director of this film.
So it makes a sub-goal.
Correct. Step 2. It generates a query and performs a retrieval action. It queries the graph and it gets the director's name, Dziga Vertov.
Okay, hop 1 is complete.
Right. Now for step 3. The agent sees this new fact and it takes another thinking action. It rethinks its plan. Okay, I have the director. Now I need to find Vertov's spouse.
It's updating its goal based on new information.
Exactly. And step 4, it queries again, this time for the spouse of Dziga Vertov, and it retrieves the final answer, Yelizaveta Svilova. Then it generates the final answer.
That iterative process is what makes it possible. It's something you just can't do with a single fixed retrieval.
Impossible.
Okay, so that clearly solves the fixed retrieval bottleneck. But training an agent to master that whole complex sequence of actions, I mean, that sounds incredibly difficult. How do you stop it from getting stuck in a loop or giving up too early?
And that is where the reinforcement learning comes in.
A third innovation.
This is the real engine that makes the whole system work. We're moving beyond simple fine-tuning. They use end-to-end reinforcement learning to optimize the entire reasoning path. Specifically, they use something called Group Relative Policy Optimization, GRPO.
Okay, GRPO. Why that instead of a more standard RL technique?
Well, GRPO is especially good for learning a general strategy across a whole sequence of actions, what they call a trajectory. It lets the agent explore different reasoning paths without the policy updates becoming unstable, which is critical when your action space is this large.
So it's learning a generalizable strategy for reasoning on graphs.
That's the goal. And the thing guiding all this learning is the outcome-directed reward function.
And this function, it must be rewarding more than just getting the final answer right.
Oh, absolutely. It has to incentivize the quality of the steps it took to get there. The total reward is made up of 2 main parts.
Okay.
The first is the format reward. This actually gives the agent a reward for following the intended reasoning structure. So does its output include the right tags like think and query?
You're kidding. It gets points just for showing its work correctly.
Yes, because that promotes structural reliability. It forces the agent to be logical and transparent.
That is fascinating. Okay, so what's the second part of the reward?
The second is the answer reward, which is what you'd expect. It measures the semantic correctness of the final answer using a token-level F1 score against the ground truth.
Token level F1, not exact match. So it's rewarding answers that are substantially correct, even if the phrasing is a little different.
You got it. It's more robust to minor wording changes. But here's the most ingenious part. The overall reward is structured so that the answer correctness is only rewarded if the format is structurally valid.
Oh, that's the connection.
That's the leverage point.
The agent must learn to structure its thinking logically to even be eligible for the final accuracy reward. It bridges the gap between the structured knowledge and the natural language output.
And by doing this, the agent learns to strategically pick the most useful parts of the graph instead of just dumping a huge messy context into the LLM, which was the original problem we were trying to solve.
So we have the lightweight hypergraphs, the dynamic agent interaction, and the GRPO training it all. What does this actually get us in terms of performance? Does it really translate to better answers?
It delivers, and the results are pretty stark. Across 6 standard ARG benchmarks, including those tough multi-hop ones like Hotbot QA and Music, GraphR1 consistently gets the highest reasoning accuracy.
And the numbers in the source are pretty clear on this. Looking at the results with the Qwen 2.57b instruct model, GraphR1 achieved an average F1 score of 57.82.
Now, compare that to a chunk-based standard RAG that was sitting at 32.05.
Wow.
Or even Search R1, which is also RL-enhanced but still chunk-based, that only got to 46.1 mic.
So the takeaway is clear. The graph structure is critical, but you only unlock its full potential when you combine it with this strategic reinforcement learning approach.
It seems so. The agent-based exploration is the key.
And what about efficiency? Did the lightweight construction actually pay off?
It did. Because its thinking is so concise and the retrieval is so targeted, it hits those top F1 scores using a moderate, balanced amount of retrieved content. It completely avoids that long context dependency problem.
And it generalizes well, too, right? It wasn't just memorizing the training set.
Exactly. They did out-of-distribution testing, and it still performed at over 85% of its in-distribution score in many cases. That shows it learned a real strategy for reasoning, not just patterns.
So the foundation is laid. GraphR1 seems to have successfully solved those 3 big bottlenecks: the cost, the fixed retrieval, and the long context problem. And it really shows a path forward for these kinds of agent-based systems.
I think if you connect this back to the bigger picture, GraphR1 is showing us that the future of RAG isn't just about having bigger knowledge bases.
It's about having smarter strategies.
Smarter, outcome-directed strategies for how these agents actually navigate and use that knowledge.
Absolutely. We've seen how solving those deep structural problems with hypergraphs and agentic retrieval leads to this huge, measurable leap in factual accuracy.
Which I think leaves a really important question for you, the listener, to think about.
Go on.
Right now, GraphR1 only works with text. It converts text into a graph. But given the massive gains we're seeing here when you combine structure and strategy, what happens next?
What happens when you extend this framework to process multimodal inputs?
Exactly. What happens when the agent has to reason across text, images, charts, and video data, all integrated into one unified hypergraph?
That is a fascinating pathway for future exploration. It really pushes the boundary of what these agents can understand about the world. Thank you for joining us for this deep dive into Agentic GraphRAG.